This is part 3 of a review of polynomial functions. If you have not yet watched part 2, you should watch that first. I will try to put a link in the upper right hand corner, or you can find a link in the description. This review covers AP Precalculus topics 1.1 through 1.6. If you appreciate this content, please don't forget to hit that like button. Number 23. The table shows values for a function h at selected values of x. Which of the following claim and explanation statements best fit these data? All of these options mention rate of change. So let's go ahead and calculate the rate of change on each interval. Here are the changes in input values. The average rate of change is going to be the change in output value divided by the change in input value. So for the first interval, that's going to be -4. For the next interval, that's -2. And then -1. And finally, -1/2. This is getting lost in the text, so I'm just going to write these down below. Let's see if we can eliminate any of these options based on this alone. The description of what's happening to the rates of change, they all say consecutive equal length input value intervals, so I can really sort of ignore that phrase. Just look at the last words. They are positive. Well, these are not positive, so the answer cannot be A. The option B says they are increasing. Are these increasing? Well, yes, they are. As we go from -4 to -2 to -1, these values are getting larger. Okay, if you put these on a number line, you would be going to the right on the number line. So they are increasing, so B is possible. C says they are negative. They are all negative, so C is still possible. D says they are decreasing. Well, we just decided they are increasing. They are not decreasing. So the answer cannot be D. So we've narrowed it down to either B or C. A long time ago, I gave you this chart which shows you the graphical relationships between f, the rate of change of f, and the rate of change of the rate of change. And I asked you to memorize it. So hopefully you did that. So according to this chart, if the rate of change is increasing, all right, I'm focusing on that because that's one of the things that is true in this problem. If the rate of change is increasing, then f of x will be concave up. So that's one thing we can look for. We also see that the rate of change is negative in every case. Wherever the rate of change is negative, f of x is decreasing. So let's look for either f of x is concave up, or let's look for f of x is decreasing. We just saw that if the rate of change is increasing, that means h will be concave up, not concave down, so the answer is B. Number 24. The graph of f is shown above. Which of the following statements about f is correct? Statement A says f is positive and increasing. Well, f is increasing because from left to right it is rising, so it is increasing. Is it positive? Well, f being positive means that it is above the x-axis. Part of it is, part of it isn't. So the answer cannot be A. Let's see. For B, the rate of change of f is positive and increasing. So when they start talking about the rate of change, I'm going to look back at the chart showing the graphical relationships between f and the rate of change of f. This chart reminds us that if f is concave up, then the rate of change is increasing. Let's take a look. F is concave up, so the rate of change will be increasing. But is it also positive? Our little chart reminds us that if f is increasing, then the rate of change will be positive. F is increasing, so the rate of change will be positive. So the answer is B. Let's do the same thing with h of x. So h is increasing, it is. and the rate of change of h is increasing? Well, the rate of change is increasing only if f of x is concave up, or h of x. H of x is concave down, so the rate of change of h will be decreasing, not increasing. So A is not the answer, and also for the same reason, C is not the answer. So it's either going to be B or D. So for B it says h is increasing and the rate of change is decreasing. Well, we already see that h is increasing. So the answer is going to be B, because h is increasing and not decreasing. Number 26, f of x equals this polynomial. Which of the following statements about the zeros of f is correct? And they're talking about how many zeros there are. So let's just state some facts that we know about the zeros. For starters, let's identify the degree. If we look only at the leading term of each factor, we can figure out what the leading term of the polynomial would be, which tells us the degree. So in other words, ignore the plus 4 and the minus 3 and the minus 1 for a minute. If we multiply all these together, we're going to get x to the 2, 4, 7, 8. So that tells us that we're dealing with degree 8. So the degree, according to the fundamental theorem of algebra, tells us the total number of zeros, including imaginary zeros and counting multiplicity separately. So we know we have 8 total zeros. One of them is x equals 0 with multiplicity 2. So immediately that means that A is not the answer. There's a total of 8 zeros, and so there can't be 8 distinct zeros if one of them is already repeated. There can't be 8 different zeros if we already know that one of them is repeated twice. The second factor is going to take a little bit of work. If I take x squared plus 4 and I set that equal to 0, first of all, it is not factorable. If this was x squared minus 4, it would factor as x plus 2 times x minus 2. But this is not factorable. What I can do is subtract 4 from each side, so I get x squared is equal to negative 4. Then I can take the square root of both sides. So that's going to give me plus or minus the square root of negative 4. This is imaginary. That negative under the radical is going to become an I. So I'm going to have x equals plus or minus I something. And then because of the 4, the square root of 4 is 2. So in fact, I think I'll put the 2 in the front. And this will be plus or minus 2i. To be clear, that's 2 imaginary zeros, 2i and negative 2i. Back to real zeros. Next we have x equals 3, multiplicity 3, and x equals 1, multiplicity 1. So these are the real zeros, and if we count them all up, so we have 2, and then 3 more is 5, 1 more is 6, and then with these 2 imaginary, that's 7 and 8. So we have now accounted for all 8 total zeros. We have 3 distinct real zeros, 0, 3, and 1. And then we have the 2 imaginary. So we do not have 4 distinct real zeros. There are only 3 distinct zeros. So B is out. F has 3 distinct real zeros, and 2 non-real zeros. Yep. So the answer is C. Number 27, the polynomial function h has zeros x equals 3, multiplicity 2, x equals negative 4, multiplicity 3, and these 2 imaginary zeros. What is the least possible degree of h? Remember, the degree gives us the total number of zeros, including imaginary, and counting multiplicity separately. So I see the multiplicity 2, multiplicity 3, that's 5 zeros so far, plus the extra 2 imaginary. However, be careful. Imaginary zeros always occur in pairs called conjugates. So if x equals 2i is a 0, that means there is automatically going to be another 0 of negative 2i. If x equals 5 minus 3i is a 0, there must also be a 0 of x equals 5 plus 3i. So that's 5 real zeros plus 4 imaginary zeros. So the least possible degree is 9. Let k of x equal this polynomial. Which of the following statements about the zeros and multiplicities of k is correct? Before I look too carefully at this, I need to factor this a little bit more. X squared minus 9 is factorable, as is this trinomial on the end. So we have k of x equals, and we can factor the difference of two squares here. So this will be x plus 3 times x minus 3. Can't do anything with that, so I'm just going to leave my x plus 3 squared. And now let's factor that trinomial. A binomial times a binomial. X squared will factor as x times x. 9 will factor as 3 times 3. Or 9 times 1. But inner plus outer must equal the middle. So it must be positive 3 and positive 3 to make positive 6. Now I'm looking for repeated factors that I can sort of collect together. So I'm noticing that we have x plus 3, we have 4 of them. We have x plus 3 squared, so that's 2 of them. And then, wait, we have 5 of them, all right? I have 1, 2, 3, 4, 5. So we can write x plus 3 to the 5th power. Okay, and that just leaves our extra x minus 3. So that means we're going to have a 0 of x equals negative 3 from this factor with a multiplicity of 5. And we'll have a 0 of x equals 3 with a multiplicity of 1. So the answer is A. Number 29. Selected values of the polynomial function g are shown in the table to the left. Which of the following statement pairs about g could be true? So I have a feeling we're going to need to analyze the changes in the input values and the changes in the output values to be able to answer some of these questions. So let's do that. So here we have the changes in the input values and the changes in the output values. Since the input value changes are all the same, we can sort of use a little bit of a shortcut and answer some of this question by only looking at the changes in the output values. Because whatever these blue output value numbers are doing, that is what the actual rate of change will be doing. Looking back at our chart, remember showing the relationships between f, rate of change, and rate of change of rate of change. If we notice that the rate of change is increasing, then we'll know that f of x is concave up. If the rate of change is decreasing, then we will know that f of x is concave down. In this case, we see that the rate of change is increasing, so we know that the function is going to be concave up. So we can eliminate option A and option C, which say concave down. To be clear, these blue numbers are not the rate of change. We can just use them like this to say that the rate of change is increasing only when the input values show a common difference like this. So we've narrowed it down to either B or D. So we just have to figure out if G is an odd function or an even function. Those are the only two options. So let's talk symmetry. So even symmetry means y-axis symmetry. So this is a quick side lesson. Given this blue dot right here, if this is going to be part of an even function, I need y-axis symmetry. So there's going to be another point, the mirror image will be on the other side of the y-axis like this. On the other hand, odd symmetry is origin symmetry. So if I have this blue point here, if it's going to be odd symmetry, there should be a mirror point opposite the origin like this. This is what odd symmetry would look like, one point at a time. So which do we have? Let's just find 2 points that should be opposites. The key is that we need opposite x values to do this. So the only 2 x values that we can really work with are the -1 and +1. So let's simply plot these 2 points. If we plot -1, -3 and 1, 3, that's going to show us whether we have an odd symmetry or even symmetry. So here's -1, -3, and here's 1, 3. So there's no way this is going to have even symmetry because we don't have a mirror image across the y-axis. This is mirror images through the origin. So that's odd symmetry. So the answer is B. Number 30. The table above shows values of the even function f at selected values of x. What is the value of a plus b plus c? So we are told that f is an even function. Let's think about what that means. An even function has y-axis symmetry like this. That means at opposite x values, like -1 and +1, the y values should be the same, like 5 and 5 again. So let's look for some opposite x values on the table. So I see the -2 and the +2. At opposite x values, the y values should be the same. So that tells us that a must be 1. If you were to graph the point -2, 1, it would be right here. If you graph the point +2, 1, that would be right here. Notice that the y-axis splits these right down the middle as a mirror image. This y-axis symmetry is needed if we have an even function. So a is definitely 1. We see another pair of opposite x values at -6 and +6. Again, at opposite x values, the y values will be the same for an even function. Since the y value at -6 is -4, the y value at +6 will also be -4. So c has to equal -4. And if we look at this graphically, if -6, -4 is right here on the graph, then for an even function, we have y-axis symmetry, so we should have the mirror image point right here at +6, -4. So that's another way to understand why c has to equal -4. So that's how we find missing y values on a table of an even function. But how do we find missing x values? Well, previously I said if we have opposite x values, then the y values have to be the same. But this is a two-way street. If the y values are the same, then it must be at opposite x values, because that's how an even function would work. That's how you get y-axis symmetry. So if we have a missing x value, all we need to do is look for equal y values, and then the x values should be opposites. Let's look for two places where the y values will be the same, because the y values will be equal where the x values are opposites. So at -3 and +3. So this indirectly tells us that b must equal +3. Let's look at that graphically. If we know that we have 2 points that have a y value of 5. So we have a y value of 5 here and here. For an even function, these have to be mirror images of each other. And if we know that one of them is at -3, then the other one must be at +3. So that's another way of understanding why b had to be +3. So in the end, we are actually being asked to find the value of a plus b plus c. So if we add these up, this is 0. Before we go on to the last problem, I want to talk about how we would handle the problem if it had said that f was an odd function instead of an even function. An odd function is symmetric about the origin. So at opposite x values, like -2 and +2, the y values are not the same, they are also opposites, like -8 and +8. Again, at opposite x values, the y values are also opposites. So at opposite x values, like -2 and +2, the y values would also be opposites, like +1 and -1. So that would tell us that a would equal -1. And at the opposite x values of -6 and +6, we should see opposite y values, -4 and +4. So under those circumstances, c would equal +4. As we look for the value of b, ignore the point that I just scribbled out because that wouldn't work for an odd function. But if we have opposite y values, then for an odd function we should have opposite x values. So I see a -4 here, so I would expect to see a +4 here. So then we would know that b would equal +4, and then the sum of all of these would be 7. Last one, number 31. The graph of the polynomial function h is shown to the left. Write 2 limit statements to describe the end behavior of function h. In really basic terms, we might say that the end behavior is falling on the left and falling on the right. Now let's translate that into limit statements. Left end behavior always starts out the limit as x approaches -infinity, because that means as we go towards the left. Right end behavior always starts out the limit as x approaches +infinity, because that means as we go towards the right. To express the idea that f of x is falling as we travel to the left, we say the limit as x approaches -infinity of f of x is -infinity. That's the falling aspect. F of x is also falling on the right, so the limit as x approaches +infinity of f of x is also -infinity. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.